All right, here we go. Let's look at this one. Atwood pulley or the modified Atwood pulley. Do you remember when we had like the table and we had a pulley? So here's a pulley on the end here, and the pulley was connected to a string that was maybe connected to, oh, remember the little cars we played with? They weren't very exciting little carts, but they were low friction carts. And then maybe we hung a mass on the side over here. Does that seem familiar? Good. All right. So let's connect them all up. Throw some string on here. Pretend like that's nice and parallel because it is totally not. And there we go. All right, I think that's all I need. Oh, we'll even put some friction on this thing. I'm going to put some slashy lines to show you that it's not smooth. Let's give it a coefficient of friction, a small one. How about a 0.1? And I'll be easy this time. We'll call this M1, and it will be 1 kilogram. This will be M2, and it will be 2 kilograms. And this little pulley is not very nice. This pulley is heavy. It's M3, and it's 3 kilograms. So, same thing. What is the acceleration of the system? And the tension in each cord. So, free body diagram is the first thing. Here's our 1 kilogram object sitting on the table there. We're going to draw our FBDs. There would be a tension force. I'm going to call it FT1. There would be a weight, FG1. There would be a normal force, F normal. And because I was sneaky and threw friction in there, and it's been so long since we had fun with friction, there's a friction force. Then we have the 2 kilogram mass, which is my triangle shape this time. It's hanging from a string over a pulley with mass, so it's going to have a different tension than the portion connected to the 1 kilogram mass. So that would be FG2. And then we have to add the 1/3 that's new. And we add in, pretend that's pretty because it's so not to the left, but there's your FT1 and here's your FT2. So, what do you think? Which way is the 1 kilogram mass that sits on the table going to move? Left or right? Up or down? To the right. So make to the right positive. What about the hanging mass? Which way is it going to move? Down. So let's make that positive. What about our heavy pulley? Rotate which way? Clockwise. So we'll make clockwise positive. Yes, ma'am. It does. We could add in the mass of the pulley. And then we would have if our pulley was being held by some rod like this, there would be like a force from the pulley rod from the axle. It would probably be at a weird little angle because it would be pushing it out but holding it up. We're not going to find that one in this case. We're just looking for the acceleration and the tensions. Okay, so let's sum our forces. So when I sum the forces in the x direction on the guy sitting on the table, just like first semester M1A, that is FT1 minus F friction is equal to M1A. When I sum the forces in the y direction on it, they would be balanced. That's our old friend, the normal force, minus the weight force on it, and they're balanced. Sum the forces on the hanging mass over here, M2A. FG2 is down, FT2 is up, and that would equal M2A, just like before. Now, summing the linear forces on this guy would be interesting because we've got X, Y components here. There would be, we would have to know this angle right there because isn't our pulley axle force at some angle? I know it has to push out and up because in order for this system to be balanced, when there's an FT to the left, there has to be something to the right. And if there are two forces, a tension 2 and a weight 3 that are down, I have to have something up to hold it up. So if I only have an axle to apply a force, it's going to have to put a force in two different directions at the same time. What's up?
So is that theta, is it dependent on the acceleration?
Nope, it's dependent on the angle of the pulley clamp arrangement up here in the picture. It would be like that theta.
Okay.
But very good question. That is not the angle that it spins through. That's the angle that the pulley arm makes to the table while it's the clamp holds it there. So if we did sum the forces in the x direction, they would be balanced, and we would have a force from the pulley axle. I'm just abbreviating that. What would that be? Sine? Nope, it would be cosine. I can do trig. Minus the FT1 would equal 0. And when we sum the forces in the y direction, we would have the upward component of the pulley. I got too excited there. Hold on. This should be 0. So then the upward force of the pulley axle, sine theta, minus the FT2 minus the FG3 would equal 0. So those are the forces, linear forces acting on your pulley. But the interesting thing is summing the torque, because the torque is going to be how we find the angular acceleration, which we link back to the acceleration of the cord. So we said that FT2 would cause it to rotate clockwise. FT1 would cause it to rotate counterclockwise, and that would equal I alpha. Okay, so now let's do some substitution. FT2, there he is. So would FT2 be the same thing as FG2 minus M2A? And FT1, would that be the force of friction plus M1A? Do you remember the force of friction, the equation? We did a lab. We determined the force of friction equation. So somehow you're going to put all those little letters together and get that the friction force is mu times normal. Friction makes physics fun. Yeah. Okay. So let's substitute our FT2 and our FT1 into these equations. So this whole dude right here, this whole thing is going to have to come over here and boom, right there. And this whole thing is going to boom, right there. So then FG2 minus M2A all times R. The most common mistake I see students make is that you get into the substitution business and you lose a letter. Like you forget the R because you're doing so much substitution. So just be careful. Now let's do a substitution. So the force of friction would be mu times normal, and normal would be mg, m1g, and then plus m1a, all times r. And then it's a disk, so 1/2 m3 r squared times alpha. So let's do some final substitution here. So m2gr minus m2ar minus mu m1g, nope, minus m1ar is equal to 1/2 m3r squared. What can I substitute for alpha? A over r. Because both strings are at the same radius. We're going to do one where they're not in a minute. All right, so what can I do? Yeah, get out that lightsaber and zoom, zoom, zoom. Oops, I had an R that was supposed to be right there. Didn't I? See, look at me forgetting stuff. I'll go back and make him blue. And then I'll... Okay, so what are we left with? Let's see. We want to find the acceleration. So m2g minus mu m1g would be equal to 1/2 m3a plus m2a plus m1a. So then m2g minus mu m1g over 1/2 m3 plus m2 plus m1 would equal your acceleration. So this would be 20 minus 0.1 times 1 times 10 over 1/2 of 3 plus 2 plus 1. And I got 4.22 meters per second squared. Do you agree, disagree? No comment.
No comment.
Okay. Now let's go back and find the tension forces. So FT1, it would be mu m1g plus m1a. So that would be 0.1 times 1 times 10 plus 1 times 4.22, which should be 5.22 newtons. The tension in the second chord would be Fg2 minus M2A, which would be 2 times 10 minus 2 times 4.22. And that's going to be a big number. Holy cow. Those tensions are way different. And the last one we did, the tensions were, a little bit off, right? 24 and 23. And this one's 5. The other ones are almost twice as much. Why? What was the big deal? What was the big difference?
Oh, they were both hanging off.
They were both hanging, but what? What was